Siddharth here. I don't remember the names, I mean the faces yet. If you could just once, no, என்னங்க இல்லையா இல்லை அவங்க அவங்க கொஸ்டின்ஸ் போட்டு வராங்க சரி ஆரம்பிக்கலாம்ல okay just quickly go around okay so I don't remember the name Somil right Lucky and Ronald okay you're Ryan Hota okay Kathakali okay and huh Sandeep Narayanan I am Bedi yes Rishikesh yeah you got it okay so and there is one Siddhant I think who he said he would join and but so let's start then thank you for showing up at 5 o'clock and I'll try to finish it and I think we are all here mostly okay 3 plus 4 plus 4 8 plus 11 Maya she plans to take the course no okay so we have to decide on regular slot okay so as I told you what Tuesdays Thursdays is what I proposed but one person probably it was Siddhanta someone I don't know had some clash on Tuesday and there was one new clash. Typically, you had a new clash at 2. It is resolved. Okay. But who had, you had, does it still persist? Only on Tuesday? What is that? Oh, that's I'm coming late into the game, so I probably can ask them to change. It's too late. 11:15. Oh, God forbid. 11:15 is. I'm pushing it later and later to avoid conflict. 11:15 would be very bad, no? I mean, what we can do is, see, I cannot do, I mean, I can't do 5, okay? I mean, obviously 5 is not a good thing, with the shuttle and everything. What I can do is Wednesday and Friday, 3:30 to 5. Okay. Huh? The Friday is what? Yeah, what? But only on Friday. How many of you are serious about taking this course? And okay, don't know what to do. I mean, if it's early, 9 o'clock, huh? What is fine? Huh? No, it has to be fine for 10 people, huh? No, I can do Wednesday, Friday, or Monday, Wednesday. Yeah, one day. No. I'm the most flexible here. Any day, any time, I will do it for you. Okay, let's do one at a time. No. We'll do Wednesday, 2 p.m., one class, one slot. Yeah. If I can pull up. Yeah, I can do that. No, but lecture, yeah. Okay. Even if, okay, this has to be done today. Therefore, I don't mind spending some time on this. I did all these things for Siddhant and he hasn't shown up. I can throw. No, but anyway, I had to record it for his convenience. Uh, yeah, I showed up. I pulled it out. So what? But you all know. Oh, okay. Since you, rather than have a lot of crosstalk, so what is, tell me. Okay. One slot is Wednesday at 2 o'clock. Okay. Yeah. Yeah, I don't know. You guys say that Monday morning, Monday morning seems at 9 o'clock. There is hardly anything here. I'm sure. Huh? Huh? Yeah. Monday morning works. Huh? So Tuesday morning is also here. It seems empty. Data sciences is not given here. Oh, Monday 10:30. No, Monday 10:30. Oh, what speaker? Hmm? Okay, Monday 10:30 is fine. Huh? Yeah, for all the 10 people who put their hands up that they are thinking about it. I mean, you're the, and I forgot your name. Yeah. Huh? Ronald. You're not, yeah, but anyway, so, I'm not going to ignore you, but 10:30 is for now. Okay, Monday 10:30, and we need one more class. How about Friday something? Huh? No, Friday 10:30 is algorithmic game theory. Okay. But Friday 3:30, you said there is clash, no? Games on graph. Uh, hmm? Okay. So, what we decided was Monday 10:30 a.m. Okay, and Friday, 2 p.m. Oh. Is Monday 2 p.m. Okay, so with this, the next class after this, today is Wednesday, I want to have it on Friday, okay? Because, I have to make up for some of these things. Starting this Friday, we'll do it 2 p.m. and then regularly Monday and Friday. Yeah? Next week, you have offline class? No, until September, 10th or so, I'll be here. Okay, and then maybe for a couple of weeks, I will then, for a couple of weeks, starting from September 10th, okay, 12th, till end of September, till like September 26th, we'll switch to the I'll be in California time zone, therefore I'll have to switch over to the online mode. And then I will have it at 6:30 p.m. your time. Yeah? Okay, when it's online. There should not be any clash. Oh my God. Okay, any questions about this thing? And we'll get more into software modeling and so on. I mean, just in this thing, what I wanted to make sure that I thought I had it shared. No? Oh, no. இது ஏன் அதுல வருது இல்ல இருக்காரா இருக்காரு அவரு சங்கர் இல்லையா it's there. Okay, வந்து Yeah, just to make sure that you understand this concept of, formulas representing, Boolean functions, which means they are predicates, and how they are, when viewed as what they denote. I was saying that they denote just set of whatever values for which that the predicate characterizes, which means for which the predicate is true. And I just chose the example of one assignment statement being modified as a transition relation. And we discussed this kind of sequence of, conjunction of a sequence of transition relation invocation, which kind of denotes a trace, okay? So anything that is satisfying this denotes a trace, and therefore this entire predicate, which is a conjunction, denotes a set of traces, which you can consider as something that is generated if this statement, okay, because each instance here characterizes one step as denoted by, of executing executing that once. And then anything that satisfies this will be from some initial state here fixed as 1, 1, okay, that you could, what you would get is it is true if after executing case steps, because they're all consecutively, they are linked together, and that ends up in a 0, 0, okay? And as though this were in a while loop. So that you understand, right? Okay, good. Yeah, I just want to, we will be talking about, this is proposition logic that we're talking about. So before we get into predicate logic, first order predicate logic, I just want to, we're talking about modeling and how you encode things. There is something in between full first-order predicate logic and propositional logic. This kind of propositional logic, but it's called pseudo-Boolean Boolean constraints. Okay, so here the variables are Boolean variables, but the constraints are expressed as linear constraints, x1, x2, x3. They range over Boolean variables. But here, you can have coefficients, linear coefficients, and the bounds. Okay, so this called when pseudo-Boolean constraints and cardinality constraints, the restriction of PBC when you have the coefficients as just as -1 and 1.
Hello.
Now, this one, since the variables here are still Boolean variables, so they can always, these kinds of constraints can always be encoded as propositional formulas. But using these kinds of this kind of a notation makes the encoding very compact. Okay. Now, for example, we looked at that seating assignment problem, okay, where most of the constraints could be expressed as exactly one, at most one, at least one kind of things defined over the variables. And if you try, I mean, I left it as an exercise for you to actually express some of those things and complete the problem. And then as one of the assignments for Z3, I'm going to show if you had the same constraints there, they could be encoded much more compactly here. So for example, so same variables, because the bool, here also I'm using the same variables to encode the seating arrangement. Person 1 and 3 shall not be seated next to each other was expressed as not of x1 2 and not of x3 2, right? So not can be expressed in this thing as 1 minus x1 2 being either 1 or 0. Okay. And similarly, so it could be expressed as something, something like this. This here, the original Boolean encoding was also quite compact. But now, when you get to doing things like every person must be seated here, so here that can be expressed that this must be at least one of those variables have to be good, so you could express directly in this fashion, as opposed to every time encoding it as propositional thing. Yeah. Try. I mean, this is at least one, no? At least one on x1, x2, x3. Yeah, I mean, not all, maybe not always, okay? Try exactly one, or at most one, okay? Some of them are certainly more compact. If you look at, you'll have to consider lots of disjunctions of conjunction and so on. Yes, not always, but in a lot of cases, it can be. That's the point I'm making. So, there are pseudo-Boolean constraint packages that are supported, okay? So where if you want to model your problem, then you can model it as PVC, cardinality constraints, and there are packages that automatically generate encodings of these things. And generating encodings for these, a conjunction of these things, or Boolean combinations of PBC constraints. And there are various ways in which you can encode these things for different subclasses of these things. And that itself is quite an exciting way of exciting problem area. Okay. So that is something that I wanted to, yeah. I mean, you can do Google search and you will find these things, but I still am giving this problem also as one of the exercises where either you come up with a, encoding, propositional encoding for, a PBC constraint, and you can Google search. But what I want you to do is whatever encoding that you come up with, either through Google search or on your own, to actually do it on Z3 and then C. Of course, these PBC constraints can be thrown at as an MILP instance, mixed integer linear programming instance, and you can solve there as well. What I'm talking about is using PBC as as a means of encoding propositional problems, and then so that your problem will be encoded, in a compact way, but then converting them and then using SAT solvers. Okay. So with this, what I want is, and I will be uploading some problems as early as tomorrow. The Z3 link to the GUI interface I've already uploaded. I'm going to upload a document which gives the a way of invoking Z3 through an API from Python or C or C++ and so on. And you can start solving this problem, especially those. I mean, this is going to be an assignment for everybody, okay? And therefore, I encourage people that have had logic also to do. Okay. Control this. What do I want to? So today, what I will cover is just to give you, I know you'll be using Z3, which is like the working horse behind all verification tools, including the 3 tools that you will be using in the course. So, but this lecture gives you just a quick overview of what kind of algorithm that goes into a box like Z3. Okay, it's a very quick, and for this I'll have to cover resolution. Okay, the resolution is an inference rule, is a complete inference rule for deciding propositional logic. It was probably covered in your, if you're taking logic course, probably it was covered, but nonetheless, I'm going to give a recap just so you will understand Z3. Now, this is just an overview. Now, if there is interest and I have time, then I can cover in one lecture more details into the technique called CDCL, which you might not have seen in your logic course. And if there is interest within the class amongst you, I can go into details. But today is an overview of the thing. So, like I said, this is how do you do this? All kinds of verification techniques that we'll be discussing will eventually be reduced into some things. So normal forms play an important role in any kind of decision procedure to decide satisfiability of in propositional logic. And what are normal forms? You've seen, you've heard of DNF, CNF, and so on. There's one normal form that you may not have heard, which is the basis for some canonical representation of Boolean functions called BDDs that I will introduce. So what is a normal form of Boolean formulas? What are the two? I mean, if there's CNF and DNF, you know what it is, but I'm trying to see what defines a normal form. Okay, there are two aspects. One is normal form is a restriction on the syntax of the way that you construct your formula. Okay, that is one. There is a syntactic constraint that defines a particular normal form. And the normal, usually it is considered a normal form if it is universal, in the sense, with those restrictions, even with those restrictions, every Boolean function that you could possibly represent, it should be representable, within that restriction. That's the semantic universality. Okay, with these two things, you can have different kinds of normal forms. DNF and CNF do satisfy that thing. So conjunctive normal form is a set of clauses. Okay, so sometimes it's called product of sums. Okay, it's a set of each of these. Okay, here there are a conjunction of clauses. So sometimes you refer to them as a set of clauses, where every clause is a set of literals. Okay, and a literal is either a variable in positive form or negated form. Okay, so this is just a two-level representation of propositional things, where the connectives that you can use are only are restricted to conjunction at the top level. At the next level, it is disjunction if you represent this formula as a tree, and the negation can appear only at the leaves. Okay, so that is the restriction. So that's what defines CNF, and this is, with these, and it is universal in the sense any Boolean function that you can ever represent using a proposition formula with any Boolean connectives can always be represented in this fashion. Okay, so literal, clause, and set of clause. Okay, so those are the three things. Is CNF, okay, I've already defined normal form. This is conjunctive normal form. Is this canonical? There's this notion of canonicity, okay? It is said to be canonical if that normal form represents every Boolean function in a unique way, okay? So is CNF a canonical form? It's a normal form, yes, they have already said. Is it a canonical form? It is not, okay? Because you can have, obviously you can, the order is not important. You can have it in different orders, and there can be sometimes some redundancy can be there, which can be removed, etc. So it's not a canonical form. The advantage, okay, normal form is sometimes is exploited, is leveraged in the way the decision procedures, algorithmic decision procedures are constructed, okay? And CNF is very important for us, and especially if you're doing SAT solving, because almost all SAT solvers, I shouldn't say all, okay? Yeah, I mean, most SAT solvers, their input is, they manipulate, okay? They implement the algorithm, the decision procedure. They expect the input to be in CNF, okay? Why? You will see resolution assumes this, okay? I mean, resolution works on CNF formulas, and since resolution became the core engine for SAT solving, and especially one particular version of resolution, and on which they have, and that has not changed. It's and that's appears to work very well in practice, and so they continue to use that. There are some set of tools that are emerging where, but even there, those tools, the internal representation of the formulas manipulated, are basically in CNF, but a different kind of CNF. They're called horn clauses. You must have heard of, they're a kind of CNF formulas, a little bit of an extension of this so-called Horn clause. Horn clause is a CNF formula in which there is at most one a positive literal in each of the clauses. Okay, but there are, to answer your question, there are some verification tools. There's one which is quite famous called Seahorn, which uses constraint horn clauses, okay, which is an extension of things. So there are, besides those two things, I'm not aware of any other kind of thing, okay? So of course there is disjunctive normal form as well, okay? So in one slide here is the complexity of Boolean satisfiability checking. This is an NP complete problem, a classic one at that, in that a lot of other problems are reduced, NP completeness is reduced to show that. But there is some interesting thing. Oh, shit. What did I do? See, if one has the formula in CNF, validity checking is easy. Okay, why? I mean, I've already given the answer. So every, yeah, I mean, checking a clause is valid only when there are, two literals with polarity. So what you have to do is to make one linear pass at it and ensure that every clause in your formula is valid, okay? And validity checking proves that if there must be one variable which occurs with both polarity in your thing. But satisfiability checking is the one that is hard when you have that it in CNF. Whereas it's kind of the dual of that. If it is in DNF, SAT is linear because they're the class. It's a disjunction of what are called cubes. Cubes are the term that is used for the negation of a clause, which is a conjunction of literals. Checking that is easy. So even if one of them, okay, if all of them are unsat, okay, then the whole formula will be unsat. So therefore, this is a linear, but validity checking is. So when one talks about Boolean satisfiability checking as a decision procedure for propositional formulas, they consider that, for any Boolean function, you should be able to do that. So, as you can see, converting from, one could say, oh, I'll convert it. Okay, so there is a exponential blow up when you convert it, a Boolean function represented as a CNF into, DNF, and that is where the complexity comes. Okay, so what are binary decision diagrams? Okay, so this one can be considered as a data structure, but this is also another normal form, which CNF and DNF are very popular, very widely heard. This I call them as if then else normal form. Okay, so here is, and here, you can put certain restrictions on binary decision diagrams, and these normal forms with certain restrictions can become a canonical representation for Boolean functions. Okay, so once you get a BDD representation of a Boolean function, then all these satisfiability checking, etc., can be done in a constant time or polynomial time. Okay, so that is what makes BDD very interesting. A lot of the verification tools, this is another popularly used normal form. Okay, I should say, I mean, some verification tools use the SAT solving. SAT solvers most 90% they use only CNF. They work on CNF because of the thing, the resolution. They're all based on thing. Partly legacy, partly it has worked. Okay, till now in practice, but verification tools. A lot of verification tools, like one of which we will be using the new SMV in their backend. They use BDDs to represent the thing. So what's a BDD? Oh, shoot, why is it? There's some resolution mismatch. Okay, so just for this, I will use it in this fashion. Okay, so as you can see, this is, I call it as if then else form. So it's a nested if then else, okay, where you can, in the Boolean condition part of it, you can only query if a variable occurs, and the then and else part, you can have another if, and at the leaves, it has to be 1 and 0. So that's what this thing says. So here, a solid edge is when you traverse that when A is true. A dotted edge is when it is false, and then you query B and so on. Okay, so this, what is the function represented by this? See, at each node, the tree formed by, or the in this case, it's a graph, okay, because they're shared nodes. So what is the function represented at C? So this should be, as I said, should be read as if then else. If C, 0. If else, it is 1, okay? So what is the function represented at C? At this point, so I said each node represents a function. And you should read it as, okay, like, in terms of if then else. So what is the function represented by this Boolean function? It's just C, isn't it? Okay. If C, it is, if not C, it is 0. If C is 1 and C. So what the function represented by this is C, okay? Similarly, there is two versions of B. So B1 says if B is true, then it is false, okay? And otherwise, it is C. So this what is the function represented by this? Not B and C, okay, and so on, okay? So you could do that, and then there is this entire BDD is is whatever function is denotes the function represented by its at its node, okay, and that's how that you do it. Yeah. No. Yeah, I mean, I simplified that if then else. Okay, you can, yeah. Um, I think it simplifies to that. Let me. At B1, it is if B0, else C. So I mean, this is how it would be, okay? I mean, if you can expand this using these two implications, and then I've simplified it, okay? So it is not B and C, because if B is true, then it will be false, therefore not B, yeah? Huh? And otherwise, it is identical to C, no? So in the other case, so you can, yeah, I mean, you can see that this is what it's equivalent to this. And, at A, it is, this is the direct representation which can be, expanded in this fashion and then simplified into in CNF in this kind of thing. Okay, so and see, the reason that this is very attractive, this BDD representation, is how do you check satisfiability once it's represented? It is very easy, no? So you just have to trace from the root to the leaf. If there exists a path from the root to 1, then it is satisfiable. Okay. And the other thing is, okay, the other question, so yes, satisfiability is, going to, just taking the thing. So the other question that, and the reason the popularity of this thing is, if you have already represented two functions as BDD, okay, then, I mean, how do you construct these things? That is where the crux of the problem is. But it turns out that if you already have BDD representations for two functions, okay, then you can implement, I mean, you can construct the BDD for the and or all these operations, okay, constructing the BDD is polynomial, okay, in the size of the size of the individual sub BDDs. You see, that makes it very attractive, okay? So you can construct very uh, large BDDs in a modular way in polynomial time, and you can check your satisfiability in things. So where is the catch? So why is Boolean satisfiability NP complete? Yes, yes. If then it's a normal form, okay? So you can see that, implication and negation with constant 1 and 0 are universal, okay? I mean, you have, so as I'm doing it, if I'm going too fast for you guys, you would have to let me know. So this is the first few classes where I will spend as much time on these things. And after that, we might be coming back to these things, but only in a quick fashion, okay? Yes, it is. You can see that if negation, and 1 and 0, implication 1 and 0 is a universal thing, because you can find out, you can define or and using these two things and negation, okay? Because how do you, for example, negation, you just flip it, huh? So it is simple. So the yeah, yeah. Yeah, I think you're getting there, but you see, here, as you can see, I'm using one thing, that the order in which the variables are queried on every path, there is a certain order, okay? With that, if you use the same order, if you fix the order in which you're allowed to query the variables, this is a canonical form as well, okay? So that is a side point that I wanted to mention. So it can represent all possible Boolean functions. It is a universal normal form. But you're right, in a way that you're right, but for some functions, for some Boolean functions, for any variable ordering, so because the size of the BDD for a particular function, it very much depends on what variable ordering you use, okay? For some functions, even the lower bound of the size of the BDD is exponential, okay? No matter what ordering that you use, let alone, even if there is a compact representation of BDD, finding out what variable ordering that you could use to get that minimal thing, that is an NP complete problem as well, okay? So therein lies the thing. So there's no thing of P is equal to NP or anything here. So, that is the reason that it is. But there are a lot of functions for which you can find variable orderings for which the thing is, the size of BDD is linear, okay? And there are lots and lots of functions that occur in practice where you can, and that's why it works so well in practice. There are certain things where you cannot, for example, multiplication. If you have multiplication over bit vectors, all that is, is very hard. They're exponential in size. Yeah, but these are, I shouldn't shake this thing at all. canonical, yes. It is, yes. For if you fix the variable ordering, that on every path, then it is canonical. So that is called the ROBDD. I said this is generally called BDD without ordering. Ordered BDD, the O stands for ordered BDD. Reduced order BDD is when you share sub, isomorphic sub parts and use, to the fullest extent. Then it can be also, that is an engineering thing where it can be further made compact, okay? Because they can be sub uh, uh, parts which are denote the same function. They can be isomorphic, okay? Then you can actually share. For example, if there are several points at which the function C is shared, then you can have it completely shared if you use a DAG. Yeah. Okay. I answered more than what you asked for, but yes. Yeah. No, OBD itself is canonical. ROBDD is just a further compression on that. Yeah, I mean, negation is constant time. Other functions are ROBDD are canonical. OBDD is also canonical. Ordering really matters. I mean, I said, okay, the most famous open source package is the CUDDD package, which is put out by a group in Colorado University. That's why it's called as CUDDD. And these things easily scale up to 100. I think this is somewhat conservative. They scale up to thousands and tens of thousands of variables. Okay. It's just that you don't hear about these things because the SAT solving technology has, leaps and bounds, has since 2000s, it has outpaced any, breakthroughs in, BDD representation that most of them, they use the thing. So that's always, okay? Let me keep an eye on time. I know we started late with all the things. Oh, it's there. Oh, the time is there. Okay, 6. We started at 5, so I'll go till 6:30. Yeah, is that fine? Yes. Yeah, so that's always okay. Now here, it scales up to uh, BDDs. It's like a space kind of time trade-off thing. BDDs there. It's once you construct it, everything is easy. But the construction, is what can stump you. Whereas here you represent in CNF, and therefore the time complexity here is measured in terms of the number of variables in the formula, okay, and the number of clauses. These are the two measures that you have. And modern day, SAT solvers can easily handle tens of millions of variables, hundreds of thousands of clauses, okay? So, yeah, as long as your problem is of that kind now, you can easily, don't need to blink an eye in using thing. And that's why these verification tools are quite, they scale in practice. Now, it used to be like even 10, 15 years ago, they used to use SAT on as single instance calls. But nowadays, SAT solver is used, in complex procedures where millions of SAT calls can be, can be made. So there are, we'll be looking at some verification algorithms that are SAT solver based, like bounded model checking and so on, which involve in making, several hundreds of thousands of calls in solving a verification problem. Okay, now there's one before I get into resolution, which forms the basis for the algorithms, for deciding satisfiability in SAT solvers. There is this notion, okay, so say enough. I mean, if you want to get Boolean functions, of course, Boolean functions, if you allow for all kinds of operators, okay, then it is compact. But if you want to reduce them to CNF, everything into CNF with this kind of a negation normal form where the negation can only appear at the leaves, you can see that pushing the negation into the atomic level at the leaves itself will cause an explosion, right? This De Morgan law, I mean, De Morgan rule, and distributing non and not, etc. The thing. So therefore, won't SAT solvers even getting your problem, which is encoded as some composition of Boolean functions, before you even can run SAT solver, you will have to put it in CNF. How do you overcome that the problem? Therefore, this is one modular encoding that it's not but almost every SAT solver uses it. Okay, so it's called Seitens transformation, and what it is here is a Boolean circuit, okay, that uses and or exclusive or. Now, if you want to convert this into CNF, you have to, as a function, output being expressed as a function of the primary inputs, what do? In CNF, you will have to completely, that is one way, okay, a direct way of doing it. Whereas what Seiten thing does is, no, okay, what it does is, it doesn't express the output directly in terms of the input, but what it does is it introduces a set of auxiliary variables, a linear number, extra variables, a linear number of auxiliary variables based on for each of the connectives in the Boolean circuit, okay? And you can represent them, without the exponential blow up. So here is the idea, okay, of doing it. Let me see. So the idea is, okay, so you do first, I will show, yeah. See that Boolean circuits, I'm introducing an intermediate variable starting with the output. This is the output, okay? And the layer before the output has two intermediate outputs, O1 and O2. So there is another variable that I do. And these are at the third level from the output are the inputs, okay? So I'm going to, and each of them, so the output is expressed as a conjunction of O1 and O2, the first, the layer before that. And then there is an OR function, okay? O1 is represented like this, and O2 is represented, O2 in terms of the primary input. Now, as you can see, these are the extra variables that I'm introducing, O1 and O2, okay? And now you can then, individually for each Boolean connective, you can, give a CNF form, okay? So this is a generic CNF form for each of the connectives that I'm using there. So I'm using equivalence, thing and so on. So now, you don't need to kind of plug in the whole thing and then instead of expressing the whole thing in terms of the output in terms of primary inputs, for extra variables, now these things I just, plug in. Therefore, it gives a lot of, once again, this is a compact encoding. It is in CNF, but I'm using extra variables to encode the intermediate inputs. Therefore, if I have to have a CNF form that expresses the output in terms of the primary inputs, I'll have to now plug in these things, okay? And then use all the distributivity laws, etc. Okay? And instead of that, this is the form that internally also it uses. Is this clear? Any questions on that? Yeah? So that's something that is interesting. And so I just want to make you aware. Yeah. Yeah, I guess what you're saying is why do it as if and only if? Is that your question? No, but because look at the way that I've represented the whole thing, the way I'm stitching it together, because I have to say that O1 is, I have to express O in terms of O1 and O2, no? So how will you do that? Huh? What is? The dot is and, okay? So if you look at the Boolean circuit that I did, each layer here represented, maybe since I didn't have that, no. This is the one that I was in. Let it go away. Yeah. So I'll have to go back to this anyway. Oh, I have so many things opened up here that I always get confused. What, you remember what the file name that I had? It's this one, I think. Yeah. So this is O. This is O1, O2. So I have to relate O1 to O2 in terms of this connective, no? So that's why I'm saying O is equal to O1 and O2. And how will you represent that? That's where the having to also encode equivalence comes. So you remember, this entire network is represented like this, okay? Yeah, yeah. Yeah, that's what I'll plugging in. This is just a top level thing. Before, I mean, this is not in CNF form, right? No, but equality is equivalence in Boolean formula, no? Yeah? Mm-hmm. You're right, you're right. Okay, so here, because this, um, you're right. Okay, okay. That's the point that you're making. But if it appears, if equivalence itself appears as an operator, okay, then you would have to do that. See, because here the operator is Y if and only if Z, okay, and then that is made equal to an X. That's why. So that's all this thing. So you're right. In this case, this itself is enough because that itself has, yeah, that's the limited point. But if you had equivalence or, for example, exclusive OR is the negation of equivalence, then you would have to have, equivalence to plug it in there as an operator itself, right? So, yeah. Oh, no, 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 no. I think I understand your question. So what this is doing is, if you were, I mean, okay, if I gave you my Boolean function expressed in terms of this thing here, how do you, huh? No, 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 that is true. But there will be several instances of that I'm in the circuit here. Okay. So if yeah, I mean, there is some time. I mean, I'm also bound by things. So I'd rather, okay, so if you can still, I mean, before you come to the board, if I can answer, a thing, then I will give me an attempt. Now, let's suppose that I'm only replacing this. Here, I'm still only using this formula to replace in here. Okay, I think you should be comparing. What I want you to compare is, let's suppose that you did not have these things. Okay, you did not have, okay, these representations, but you were expressing directly O in terms of A, B, and C. Okay, that is how you would normally express if you want to input that formula, that Boolean function represented by my Boolean circuit that I've given there. If you want to express directly in terms of and or and not, you will have to implement the expand your thing, and that too I'm not allowing. Asking you to, it has to be represented, or it has to be represented directly as a function of only A, B, and C. Your input variables in CNF form, as it goes to the SAT solver, has to have only variables A, B, and C. Okay? Then, not only would you have to, if there are several instances of, exclusive ORs, okay, and equivalence and other kinds of functions, I mean, you will be then you have to create as many copies of those, those things and so on, right? And then push everything in terms of A, B, and C. Yeah. Whereas here, I'm introducing intermediate variables, okay, that represent that Boolean function right at that point. Yeah. So, so I am reducing the by adding those variables, I don't need to propagate, okay, kind of squash that boundary, okay. And I think a good exercise for you, maybe we can revisit in the next class. Try to come up with a CNF form for that Boolean circuit directly represented in terms of A, B, C, the primary input variables, okay? And now I've shown you how you can do by introducing intermediate variables. I think this is an exercise that's worthwhile doing for all of you, okay? So there, what you have to do is you have to kind of, plug in those things, and then you have to, in order to get it, you'll have to use distributivity laws and so on. Whereas here, you don't need to, okay? That is the difference, yeah? Yeah. Okay. So, yeah, if you're still not satisfied, we can, next class, we can do this. Yeah? Okay. So what the primary, I mean, the algorithm that goes into, that is the basic version of the core algorithm in a SAT solver is called DPLL, okay? Before I get to that, the DPLL itself is based on this resolution principle, okay? For those people who have taken logic, you've probably seen, I'm sure you've seen this, okay? So, for others, watch, okay? So this has this rule. If you have two clauses, okay, in which two clauses C1 and C2, by the way, a clause is called unit. Okay, this thing that I've not used, if it has a single literal, it's non-unit if it has more than one literal. So here this is a rule where C1 and C2 have more than one literals. And at least one of the literal appears with opposing polarity, okay, in these two clauses. Then the resolution principle says, then you can, if you have those things, I mean, assuming that it's a conjunction of C1 and C2, those two clauses, then you can resolve those the pivot variable C, which occurs in polarity, and you can obtain a resolvent, which is a union of the rest of the clauses in C1 and C2 other than C, okay? And what it says is this C1 and C2 implies R. Okay, that's all that it is saying. That is stated, and there are two other instances of it. If C1 and C2 happen to be unit clause, okay, with opposing polarity, okay, then this rule will look like this: A and A naught, A comma A bar. Then we say that results in an empty clause. An empty clause is like false. Yeah. So this is, this is contradiction. Huh? And there is also, so this is the important version of it, that you can always derive this resolvent from your original set, and then you can add this, because this C1 and C2 actually implies R, and that's what this thing says. It is called equisat, okay? They're not equivalent. C1 and C2 implies R, because this does not have that variable C there. So it says whenever C1 and C2 is set, so is R, okay? And vice versa. You can see that why that is the case, okay? So if R is satisfiable, then it has to be one of B I's or AI. I mean, one of B I's or AI should be satisfiable. Then, of course, this one, if BI, then C would be satisfiable. Then I can always make C1 and C2 satisfiable by choosing a appropriate value for C, correct? Yeah. If R is satisfiable by virtue of only some AI being satisfiable, then I can choose in the original C1 and C2, C to be 0. Okay, so they are yes, that's how they're satisfiable. Now, equisat also means that if C1 and C2 is unsatisfiable, then R is unsatisfiable as well. Okay, but in this case, the only way that C1 and C2 can be unsat, if they're not unit, if they're not unit clauses, C1 and C2 is always satisfiable, isn't it? Correct? Because if you have a conjunction of two non-unit clauses is always satisfiable. That's why the case where this being unsat doesn't arise, that is the case that is handled by this empty rule, A and not A, okay? And don't just nod your head. I mean, why is C1 and C2 two clauses always satisfiable, even when you have this kind of seeming contradiction with a variable occurring in a different polarity? Because I can always pick, regardless of this, some, one of these variables to be true and another variable to be true. There's more than one choice, for you that is available there. Yeah. As a matter of fact, there is another easy case for CNF, for satisfiability check. That is, if you have a whole set of clauses, and if every clause in the formula, if every variable in every clause appears only with unique polarity, then the entire thing is always satisfying. So imagine, so if in every clause a literal occurs with unique polarity, that means there are no clashes of C and C naught, then also it is always satisfying. That's another easy case. That's a side thing. Okay, so that's what simple resolution principles say. So what it does is it looks at two clauses, and what looks like a potential conflict between the two, it is eliminating. Okay, that is its idea. Yeah. Now, and here is the most important theorem. Okay, that is the basis for DPLL or any algorithm, that is based on resolution for satisfiability checking. It is resolution, just that one inference rule is complete, okay? That is complete for satisfiability. It's more precisely, refutation complete, that if a set of, a set of clauses, any number of clauses, yeah, is unsatisfiable, if it is, there is a, there's contradiction somewhere, that there's no satisfying instance, then repeated resolution, you keep applying these, by applying repeated resolution, you can always derive this empty clause. Okay, that is what this meaning of what it means for resolution to be complete. Okay, so is it the statement clear? Okay. So this gives an algorithm, okay? A naive, algorithm. So what you do is select a pair with complementary literals. Select a pair of clauses which have that have a literal occurring with different polarity, and you apply the resolution inference rule. Okay. And then if they're both unit and they're occurring polarity, you have a contradiction right away. Otherwise, you apply that. And what is the resolution says? It eliminates that opposing thing and takes the union of the remaining literals in the two clauses and makes it into a single clause. Okay. And you have to keep repeating this. Okay. So each time you get a new resolvent, and the resolvent, the R, will have one fewer, okay? It would have eliminated one a pair of opposing literal, okay? And therefore, and that's what this says, okay? You repeat until you either get an empty clause or there are no more new resolvents, okay? I mean, it's saturated with getting all resolvent, okay? Then if you have the resulting set of clauses, the original and the new clauses is closed, okay? That is, you cannot apply that resolution step anymore, okay? The starting point is a set of clauses. That's what you want to decide, whether it is sat or unsat. So you keep applying this. Then, it's only, when it terminates, it's only one of these two possible things. Why? Okay, so the question arises, why should this naive algorithm terminate? Huh? No, you're chicken and egg, okay? I mean, it will be complete only if it terminates, okay? Yes, when it terminates, I'm saying these, of course, these are the only thing. Either there's empty clause or there's no empty clause. Okay, that way it is, it's clear. But if it does not terminate, okay, why should it terminate? Because you start with a finite, your formula is finite. That's the assumption, okay? And it has finite number of variables. With those two assumptions, each time your application of a resolution is eliminating one, pair of, clashing literal, right? And so the new resolvent that is getting has one fewer thing that I already mentioned. So, there can only be finite number of clashing literals, and therefore it has to terminate, okay? I mean, by termination, you have to be somewhat not stupid, okay? You can keep regenerating the same resolvent. I'm not saying you have to look for whether you're generating any new resolvent, okay? So when you're not generating any new resolvent, that's when you stop. Therefore, it has to stop, okay? So, yeah, that is what is called Davis-Putnam algorithm. Okay, this was the original resolution inference rule was designed and invented by Robinson. Okay, maybe he came with and he, along with Davis-Putnam, I think they came up with this procedure. It is the first version of an algorithmic decision procedure for deciding Boolean satisfiability that came around 1960 or a bit later. Okay, DPLL that I will talk about, and that will be the last part of the thing here. But yeah, so I will show an example, okay, for you, so that this resolution, this is called a resolution graph. It shows, I can call this as a resolution proof, okay. It shows, step all the sequence of resolution application that derives a contradiction in this case. So here's a set of things, okay? So these are a set of clauses, input clauses. So as you can see here, P and B naught, okay? You can resolve on the pivot variable B, and then you get A or A, okay, which is A, okay? Similarly, you can do from here, and then you can get, immediately get a bottom, okay? This is not the only way to get a contradiction. This is kind of the shortest way to do. You could have done resolved over these two things, then you would get B or C. Then you could do C or C naught, okay? But eventually, what is in this case, you see, this subset of your formula, because it has only two clauses, it's always satisfiable, okay? There's no contradiction there. There are subsets which are satisfiable with any formula. Even adding this, there is no, you can't get a contradiction. So this subset of your original formula is satisfiable. It's only when you add this, it becomes unsat, okay? As a side note, I'm saying given any CNF formula, okay, the subset of the formula, as a subset of the original formula that makes it unsat is usually called an unsat core, okay? And the smallest such core subset is called the smallest unsat core. See, this is very important, okay? And there are, in verification, like verifying some property, etc., correctness property is reduced eventually by all verification tools reduced to verifying some formula, okay? The unsat core, here I'm sidetracking, the unsat core gives an idea of why, some kind of a smallest explanation and insight into what is causing the unsat. And this one has relationship to with kind of why a design. Suppose there is an error in your design, okay, which is manifests as a result of your formula being true. Now you can use the unsat core to get some idea of locating the bug and so on. It's a very interesting analysis that is done. And SAT solvers can give you that, if not the smallest, at least some small unsat. But that's a side thing, okay? So you understand, okay, how the resolution thing is done. In this case, it is there. Now, what I want to do is just because maybe you look at, it's important that what this completeness rule says is it's only okay. So if you only do all resolution steps involving these three clauses, obviously, since that is not unsat, you will not get things. And you should not go home, okay, saying, oh, I was not able to. So you will have to look, you have to proceed with that thing until the set that you get is closed, okay, that there are no more resolution step resulting in new resolvents. Only then, if it is, that you still cannot get an empty clause, then what that completeness result says is ensures the thing. So here is another example where, this thing is satisfiable, okay? So after these two steps, of resolution, there is no more. Okay, resolution possible. Okay, that gives new resolvents. Okay, when you're another important thing. So what I mean, you see, you're keeping the original clause. I mean, in order to get this closed set, okay, here you're seeing that, okay, these two are resolved to get this new resolvent. So the resolution step is not just, it is not just applied to the original set of clauses. So you have to consider all possible clauses between original set of clauses, between a new resolvent that you get and the original set of clauses, as well as between two resolvents that are produced. Okay, so you'll have to do that, completely, before you do it. In this case, after these two steps, you're not getting, and therefore, this is in some sense, okay, even though there are clashing literals, in this case, you are able to eliminate them without deriving an empty clause. Okay, and the reason this is, why is this, I mean, it is sad, is because, see, all these are implied clauses. Okay, and you can see the set of, there is always, when it terminates like this without getting an empty clause, there's always a subset of this closed set. There's always a subset of this closed set, the set of clauses, in which there is no, it is satisfiable by virtue of the fact that every variable occurs with unique polarity. That's why that is somehow saying, it is saying, oh, I've derived all implicants. Okay, every new result that I can imply from the original set of clauses. None of that in conjunction, whole conjunction of it makes it false, and that's why in this case you could say that it is indeed satisfiable. Okay, so, and then when you get this thing, you can choose the set whatever that you, for each of these variables, okay, the appropriate things, and that gives you the satisfying instance. Okay, so it is 6:30, so I'm going to raise one thing. Okay, I'm not going to be able to complete it today since it's getting late and dinner time and so on. So I'm going to show you why is this true. Okay, why should resolution be is complete. Okay, I want to show the proof of that, and I will do that. I will start next time. I mean, the reason that I want to show the proof is it's handwritten. I have it here. I'm not going to do it today because I want you to be a little bit more. Okay. The reason I want to go through this proof, even if it means, I mean, I will upload it. You can go faster if you did. So I will tell you one thing. Okay, we'll be doing proofs. Okay, in this class. Okay. I mean, we will discuss a lot of algorithms to do verification. Yeah. And this completeness and soundness is applicable to all those things. All of them can be considered as some kind of a decision procedure for checking the satisfiability of some formula. Okay, that is relevant to that application in a certain way. So this question of whether an algorithm is complete and sound for that problem that it's trying to solve is a repeated, a constant theme that comes throughout the thing. Okay, so for some of them, I will be presenting proofs. Yeah, and most of those proofs are proof by induction and proof by induction. Therefore, I I know if you've taken logic course, you would have seen proofs by induction. You would have already done proof by induction. I don't expect you to do inductive proofs, and there are, maybe in some pencil and paper exercise you will do, but not, there'll be lots of other kinds of things that will happen. So you don't need to get scared that you do, but you still want to be able to listen to an inductive proof and be able to understand it. And maybe some simple inductive proofs you may want to, I may expect you to do as well. So for that reason, I want to present this proof. Okay, this is kind of how I've written it. Maybe I'm sure completeness of resolution, there will be hundreds of different proofs that you can read as well. I mean, this is something that I think, and I want to mainly to illustrate what it means to do inductive proofs. But I just want to just end with making these claims, and I want to understand. So this we have already, some of it we have already seen. A single claim one, a single clause is always sat, right? Why? Because a clause, a single clause is always sat. I mean, you could pick this or this or this. So you can make any literal true, and that is thing. So claim two, I've already seen. This I already stated, yeah. So that is fine. Is that the only claim I have? Yeah. So what does this lemma say? Suppose F is a set of clauses which is pure, okay, which means C is, F is a set of clauses which is pure, means that pure means every literal appears in with single polarity, okay? That is my starting point. Into that, I will add an arbitrary clause, C, okay? When I do that, this is what I have to prove. This will be the basis for proving the completeness. So this is, F is always satisfiable, okay? Because that has a set of clauses which is pure. Into that, if I add an arbitrary clause where some of the literals can clash, it can make it, keep it sat, or it may be unsat, okay? Then I'm saying if it is sat, then I'll not, it'll, when I get the R closed, it'll not have the empty clause, yeah? Which is what the basis for the completeness thing. If it is unsat, then when I derive all the thing, R closed that I get, it will have the empty clause. Okay, that's what I'm going to prove. I'm going to prove by induction on the number of literals in the clashing literals in C. So that I will use to show just a sample of an inductive proof. Yeah. Yeah, I think, I mean, F pure is just says that a set of a formula has, is a set of clauses where every variable occurs with unique polarity. Okay, R resolved F union C, I define it as it is resolvent closed, and there is a subset of that. Okay, either that has the empty clause. If not, there is a subset which is pure. Okay, that's how I define. Yeah, I don't have the actual definition of R close, and that's how I do. Okay, pure is independent of closure of resolvent. Yeah. Okay. So we're meeting on Friday at 2 p.m. Yeah.